Welcome everyone to our webinar on From Spectroscopy Data to Reusable Knowledge. So this webinar is about spectroscopy. Okay, just since I know from the seeing the attendees, it's a diverse crowd of people. Let me remind you, we are talking about spectroscopy, where you use some type of microwave, radio frequency, or light to investigate properties of molecules or materials. And what you normally then see is a spectrum like this, where a lot of stuff happens, as you can see. I mean, all these peaks have some type of information. It can be even more than that. And what we're going to talk about is how to make this reusable or usable, but also how to take old data that is lying around in some form where you have this spectrum and how to bring it to a form that you can reuse in the present. Since we also often at HKS talk about quantum computing, let me point out that we are not really having anything about quantum computing in this webinar, but we will show at least one Hamiltonian throughout, so maybe that is of interest. All right. HQS, let me shortly introduce HQS also a little bit more. We make software for spectroscopy, where we do a simulation based on quantum mechanics of spectra in different regimes. We are specialized on nuclear magnetic resonance, but we also do, for example, UV-Vis or IR. And of course, all of this software and this working on this data and on this spectroscopy always comes with the need for structured and well-sorted data workflows. And what we often find is that actually a lot of data is lying around. Many companies on the internet, everywhere, there's a lot of data, but normally it's trapped in various formats. A particular one is, of course, PDFs, and we will have some discussion on that. Then, of course, for NMR devices or any spectroscopy device, there are the vendor-specific files. And reusing this smoothly, but also comparing this can be quite difficult. And that is what we want to talk about today, how to do this. And, out of these steps, I mean, I guess these steps are pretty self-explanatory to some extent, but one might not be self-explanatory, and that is the parameterization. Parameterization is, of course, to some extent well known, but of course, you can also automate it or make it more thorough. So let me also explain a little bit what we mean when we say parameterization. You can, of course, always keep, for example, a full spectrum, as I've shown before. But instead of keeping this full spectrum, it has always been the case that people already looked at information that is in the spectrum and keep only that specific information. And let's say in IR, it's pretty clear where you keep like the oscillation frequencies, or in NMR, where you keep chemical shifts. So these are typical properties, parameters, which you keep out of your spectrum. However, you can extend this with slight extension. You can easily also store very clearly defined parameters while also reconstructing at any moment the complete spectrum itself, but also reconstructing under different conditions than you originally took it, which can be quite useful. But before I go further into this direction, let me just point out that, of course, if you keep the parameters and you measure something new and also keep parameters and so on, it's, for example, much easier to search. That is, I think, obvious. If you compare, for example, if you would like to search a database of fully kept spectra, where you kept the full kind of frequency range of the data, searching this or make this searchable would be quite a challenge. Comparability would also be quite a challenge. And so through this, you have a much easier reuse. That said, actually a key point for what we discussed today is also reuse. So let's say you have these parameters, you kind of take your data, you extract these parameters. What does that mean actually for reusing them? And this is why at the bottom of the slide, I wrote the sentence raw spectra remain important. Of course, you should always keep your pure spectra that you measure. But if you extract parameters, then you can much easier reuse this later and automate this and other features you can do with this. And there are two specific spectroscopy modes that we are going to discuss. One is UV-Vis, where we are going to discuss a case where, for example, you can take a spectrum, extract parameters, and reuse it under different conditions. For example, if your line width of your spectroscopy increases for various reasons, maybe also device-dependent, measurement device reasons. This is like one case. And the other case is nuclear magnetic resonance, where, for example, you can take single compounds and extract very precisely their spectrum, and then extract parameters from that and reuse this later, for example, in automated analysis of mixtures. And with this, let me give you the outline of the further presentations. We will have one presentation on data rescue from scientific figures. So here the original data comes from actually a PDF. And then it will be UV-Vis data, and we will see how to reuse the same data in UV-Vis or for UV-Vis spectroscopy. Then comes a bit of a discussion about our also other software tools we have at HQS, which are about taking NMR data and reusing it and kind of converting it and so on. And then also how to reuse this data for mixture fitting, as I already announced. And at the very end, I will actually talk about really a complex set of data and kind of how you can recover it or how we did recover it, and maybe as an inspiration of what's possible in terms of data conversion and all data recovery. All right. And with this, I'm actually done for now. And next up is Vladimir Rybkin, who will talk about data rescue from scientific figures, but with a focus on UV-Vis.
Good afternoon, everyone. I'm Vladimir Rybkin from Innovation Outreach Team at HQS. I will tell you about what I believe is physically meaningful fitting of UV spectra, which are first rescued from papers, namely from PDFs. Before we delve into the technicalities, let's go to the roots and look at the electromagnetic spectrum. From gamma rays, the most energetic, to long radio waves, the least high frequency those. And then to the right, I have plotted a molecule in a very schematic way with the nuclei in the center and electrons rotating around them in a Bohr-like fashion on the orbits, which is of course not true, but it is instructive. Therefore, one can approximately separate energetic levels of the molecule into electronic and nuclear. Electronics stem from jumping of electrons from orbit to orbit or orbital to orbital, if you use quantum chemistry terminology, and the ones from the nuclei are actually rotational and vibrational. So atoms actually vibrate around the equilibrium point, and this produces spectra. What is interesting here is that electronic transitions are more energetic, so they have larger quanta and therefore correspond to wavelength lying in ultraviolet, and visible spectrum. So electronic transitions are responsible for actually what we see with our eyes, but not only this, also for ultraviolet absorption. And vibrations of molecules correspond to infrared range. So if you irradiate a molecule with heat, with infrared irradiation, you will see vibrational spectrum. And if you irradiate it with ultraviolet or visible, you will get electronic spectrum. The good thing here is that, or interesting thing here is that infrared radiation is unable to excite electronic transition because it's simply not energetic enough. But the opposite is not true. When we excite electron from level to level with ultraviolet or visible radiation, we also excite nuclear vibrations. Therefore, in the electronic spectra, in visible and ultraviolet range, we also see traces of vibrational spectra in the infrared. Later, I will show you how it works. Therefore, we have purely vibrational spectra in the infrared range, but never have pure electronic spectra, although this is a used term. Instead, we have this vibronic, which is vibrational plus electronic. So this ugly black band is electronic band corresponding to electronic absorption. But it consists of small, narrower lines which correspond to vibrations. And these lines are called fine structure, and these differences between the lines correspond to quanta of molecular vibrations. You can see this sharp fine structure only in the best experiments and typically in the gas or in matrix isolation. In solutions or at high temperatures, you see these bands, but their shape is not random. It's, of course, defined by the fine structure. So far, so good. Is it at all of any use other than fundamental? Yes, it is. Ultraviolet and visible, or actually electronic, spectra in analytics are ubiquitous due to their high accessibility. The devices are really cheap, so the low-tier device can be bought on AliExpress for a few €100, and it will be useful, actually. Of course, the better ones can cost 2-3 orders of magnitude more, up to 250K euros, but even this is cheaper than average high-field NMR device. They're also simple to use. They don't need any cryogenics. They stand on your desktop and you put a flask of your chemical inside or a pellet and you get your spectrum. So it's simple. They provide quite much information, but maybe not excessive. You will see why from the line shapes. And it needs to be informed with good physics or quantum chemistry. An important thing here is that UV blocks are used as standard detectors for high-performance liquid chromatography. So if you are working in the lab, you may have seen this. So there are several blocks of chromatographic columns. And the highest block is typically a UV detector. Then it can be also coupled to mass spectrometer, but not necessarily. So it's a very common analytic tool. And therefore, it's good to understand, reuse, save, and recycle UV's data. For that, we need first to retrieve or rescue the data and then to feed it meaningfully. We can do it twofold. The most common method is to feed them with Lorentzian functions, which I show on the right. So these are simple symmetric functions based on some simple physical models of broadening, and they don't incorporate any fine structure. It's just believe that electronic transition is one line parameterized with a simple function, having 3 parameters: A, the intensity, so the height, x0, the center position, so the absorption maximum, and then half width is half maximum. As simple as this. Instead, we can try to incorporate fine vibronic structure into the spectrum, into the fitting function. This is called the Pickarian function, called after Professor Peckar, who has invented this or introduced it. And this function is, in fact, an exact solution for the line shape of a very simple vibronic model. It's more involved. It consists from this Poissonian distribution times Gaussian function. So what is this Poissonian distribution? It's a distribution of the vibrational lines within an electronic band. So I show them here with sticks. And we have a few more parameters. So this Huang-Gris factor justifies the difference of molecular structures in ground and excited states, and a few more some global corrections. Interesting thing about these functions is that they have 6 parameters, and they are symmetric, and they, like one function can have many maxima. Well, actually, in the general case, it does. So it's more flexible, but more complicated. Now let's apply this knowledge. I have a paper with nice theoretical approach, which I widely explore in this talk. And this is tested by experimentally recorded spectra. Although the paper is new, there is no data accompanying it. So there are some data, but there is no table of the UV spectrum. And there is no electronic file, nothing, only plots on the PDFs. And I want to analyze it. What I do, I use a tool developed at HQS called Gibbon. And it's based on artificial intelligence, which extracts the graph from the PDF and produces a table. That's how it looks. I upload a PDF and select my molecule of interest and try to extract the data. So this is the molecule, DPA, diphenylanthracene. Anthracene is this 3-ring group, and diphenyl means 2 benzene rings above and below. This is the plot. Above is the plot from the paper. Below is the table data which I was able to extract. Looks pretty decent, although there is a bit of a kink here. But as we will see, it looks well enough. And before we try to apply 2 of our fitting procedures, let us ask ourselves a question. What do we see here? Do we see 1, 2, 3, 4 peaks? Are these vibronic data, or are these purely electronic lines? Maybe anything. We don't know. That's what I mean by having things informed, well informed. We may try to distinguish it by actually performing the fit. And that's what we see. To the left, Picarian function. To the right, Lorentzian fit. I use only 2 Picarian functions and 4 Lorentz peaks. 4 maxima needs 4 Lorentz peaks, and Picarian functions can be more complicated. So what is better? If you just look at correlation, then Picarian is better. Yes, it's 0.999, and Lorentzian is 0.988, which is also good, actually negligible, but Picarian is a bit better. And both use 12 parameters. Each Picarian function has 6, each Lorentzian has 3, so both 12. What does it tell us? It does tell that we have only 1 electronic transition here and another electronic transition here and 4 electronic transitions here. So that's a very different physical picture. So how many electronic oxidations we actually do have? In fact, we have 2. And these are vibronic lines. How do we know this? We performed quantum chemical calculations and found out that in this range, we have only 2 excitations. So I think I was able to convince you that this one, Picarian fit, is not only more physical, not only more accurate, but also more physical. One may say, so what? If I do mundane analytics, I don't need to know whether the line is vibronic or purely electronic. I just need to know where the maximum is. The maxima are correctly defined everywhere. Well, that's true and not true, because having good physical model allows us to reuse the data and acquire more information. As I said, the distances between vibronic peaks correspond to the vibrational frequencies active in this spectra. And these differences indeed correspond to carbon-carbon stretch. So by looking at the electronic spectrum, or UVs, which is supposed to be pure electronic, we actually define 2 vibrational frequencies. This may be useful for data retrieval and for further investigations of the infrared spectra. And this is quite good accuracy, actually. Then we may transfer this data from device to device or from condition to condition. Why? Because conditions are encoded only in one parameter out of 6. Everything else depends almost purely on the molecular structure and the nature of the molecule. Therefore, what changes is only this. To the contrast with Lorentzian functions, everything there depends on the molecule and on the environment. So here, by changing one parameter, we can fit to different experimental parameters, or actually reproduce them if you know it from another source. And the example I like most is predicting of fluorescence spectra. That's a different experimental conditions. That's also electronic spectrum, but not absorption of light, but emission of light at special conditions. And in the simplest approximation, fluorescence spectrum is obtained by inverting the band. If our band is a Picarian function, then its inversion gives non-trivial result. I mean, we need to invert each of the bands, and we have 2. Therefore, this fluorescence spectra doesn't look like a mirror image of absorption due to the presence of the 2 lines. But if you did the same with Lorentzian functions, which are totally symmetric, then you would get the same spectra. So it's actually not allowing to predict any fluorescence at all, because it's not physical enough. With this, I'm about to finish. I was trying to talking to you that ultraviolet and visible spectroscopy is an important tool in analytical chemistry. That one can rescue data from PDFs, old PDFs using Gibbon, which is developed by HQS, and we are looking forward to seeing your response, whether it's interesting for you. And finally, fitting functions to more physical models, which is actually a new trend, can allow retrieving compact and physical representations, which can be recycled for further chemometrics or chemical analysis. And thank you for your attention. I'm open to questions if there are some.
So at this point, we can just continue with Nicholas with similar idea, but now for nuclear magnetic resonance.
All right. Thank you, Vladimir. Thank you, Michael. I'm Nicholas Vogt, also from the Innovation Outreach Department. And before we use the rest of this webinar to discuss the more technically challenging and interesting aspects of mixture analysis and a more complicated example from Michael, I would like to take a step back and talk to you about the importance of references, what references actually are, physical and digital references, and how they are related to this extraction of parameters, this parameterization that Michael already introduced before. And for that, I would ask you to imagine for a moment that you are the person responsible for a chemical, for a pharma production line. And maybe there is somebody in this webinar for whom this is actually true. Anyway, so imagine you're responsible for monitoring the production, for assuring the quality. And one way you can do that is sketched in a very broad terms on this slide. So, of course, after production run, you can always take a physical sample of a batch that you have produced. And then what you need to do is you also need to procure in an independent way a physical reference. So really a physical reference sample where you know exactly what's in there. And what should be in there is what you want to produce in the right quantity. And one way to make sure that this reference really represents what you want to produce is to either have an independent manufacturing in-house where you make sure due to the manufacturing process that you know what's in there, or maybe more common to buy it from commercial vendors like Merck or government entities. So this is your reference, your gold standard, and you now have 2 physical samples. And then you both measure them with the same device, with the same parameters. And measurement here is really a very general concept. So you could measure UV spectrum, you could measure an infrared spectrum, or you could measure a nuclear magnetic resonance spectrum. So you measure with the same device, with the same parameters for comparability, you get two measurement results, and then you compare them. And ideally, this comparison should not just be an optical comparison where you check if they look similar. You should have some quantitative checks. And if all of the checks that you have defined pass, then you say, okay, with respect to this reference and to this comparison procedure, my physical sample matches the reference and I have produced the correct product. And if the checks fail, then okay, you obviously have a problem in your production process. And the details here and how strict all of this is, of course, completely depend on the risk factor of the production you're looking at. If you're running a low risk chemical production where it's not too bad if you have some deviations, then you can be relatively lenient with the quality of the reference. You can be a bit more lenient on how you measure, what criteria you use when evaluating the comparison. However, if you go to the other direction and you look at something like pharma production, which is of course highly regulated, then all of this is needs to be certified. So you need to buy a physical reference from known certified vendors. It needs to reach a high quality. You need to certify how you measure. You need to certify which criteria you use for the comparison, and so on. So it's a lot of effort, but it's worth it because this is the way you can make sure that for something like pharma, where you can really hurt people if something goes wrong, you can reach the quality standards that you need to do. However, of course, producing physical references often to a very high quality standards is a lot of effort, which means it's very expensive. Also measuring basically twice the amount of samples is also extra effort and is expensive. So this is not ideal, and one would like to streamline this process a little bit. And this is where the recent push in the direction of digital references comes from. So quite a lot of people are pushing this direction. A big entity that pushes for this is, for example, the US Pharmacopoeia, and there have been quite a few publications on this. And the background is that with the technical advances in the measurement devices, it now becomes more and more feasible to compare earlier measurements, maybe even measurements on different devices, with measurements with other devices, because there's just less deviation nowadays. So how this quality assurance method is now modified when going from a physical to digital reference is that we do exactly the same thing with a physical sample. So we collect it, we measure it, we get a result. But instead of procuring an additional expensive physical reference, one in the end simply looks up a digital reference. And this is also where we see the connection to the parameterization that Michael introduced at the start. This is exactly the parameters, or the digital reference exactly consists of these parameters that describe our spectrum and then can be used to compare to our sample result. And again, the requirements for this digital reference will strongly depend on the area you're in. So for pharma, again, it's very regulated. You will need to probably get a digital reference from a high quality database. But for low risk processes, this is also one of the points where you might be able to use some data you might already have been lying around, where you have already measured spectrum and you can, for at least some purposes, construct your own digital reference from them. All right, so that's in broad strokes what references are for. Now, and this is pretty much independent from what kind of measurement device you're using. Now let's look a little bit more specifically at nuclear magnetic resonance and how we can construct such a digital reference, such a parameterized measurement for nuclear magnetic resonance. And as Michael already mentioned before, if you have such a complicated spectrum, as you see here, you want to parameterize it. You don't want to use the full thing for the comparison. And the way to parameterize this for nuclear magnetic resonance is the well-established approach of QMSA, quantum mechanical spectral analysis. And the fundamental idea here is to link the observed spectrum that you measure back to the fundamental physics that give rise to the spectrum. So the spectrum that you see in NMR is completely defined by the spin Hamiltonian of the nuclei of the molecule you're looking at. And you can see the Hamiltonian down here. We don't need to go through everything in detail. The important thing is that it is characterized by two sets of parameters, these delta J, which are called the shifts, and these Jij, which are called the J couplings. And once you know them, you can construct this Hamiltonian and exactly predict the spectrum that you would obtain from an NMR experiment. And you can predict different spectra for different magnetic field strengths. And a quick side note, the main topic of this webinar is spectroscopy, but I know we always have a few fans of quantum mechanics in general, quantum computing here in these webinars. And of course, you can immediately see once you run this QMSA procedure and you obtain these correct parameters here, then you can always construct the correct spin Hamiltonian for an NMR problem and can use it as input for, in general, quantum simulation, or more specifically, a quantum algorithm, if you want to go in that direction. However, back to the QMSA approach and the parameterization. So what you essentially do is relatively simple. You have a first guess for these parameters, for the shifts and the J couplings, and then you can plot or calculate the corresponding spectrum, and you then can compare it to an experimental spectrum that you have recorded. And then what you do is you just implement a fitting procedure that fits these parameters in a theoretical model to the experimental result until they match, or mostly match. And through this fitting procedure, you get the parameters, you get the parameterized digital reference for NMR for a specific molecule. All right, so this is, in a nutshell, in a very brief summary, how QMSA works for getting digital references for NMR. Before I hand over to the mixture discussion, however, I want to say a few words extra about something that's very important if you want to recycle old data and maybe not ideally preserved data for this kind of QMSA procedure, or in general for working for post-processing NMR spectra. And that is that you need to do quite a bit of data cleaning before you can actually execute this QMSA procedure. So what we're going to look at is how would you need to process some experimental data that you might have imported from a paper to be ready for this QMSA procedure. And the data that I'm showing is going to be artificial. So I made it artificially a bit worse so that you can actually see some of the corrections that you might not necessarily see. They're necessary, but you might not nicely see them in plots if I don't do that. All right, so first thing that you might need to do is the frequency axis correction. So what you can have is that the data that you read in, that's especially the case if you, for example, use a tool like Gibbon to read in data from just a graphical representation of PDF, you might be off a little bit with the frequency axis, but it can also happen with data in another format. You're just a bit off. You don't fit the frequencies correctly in the x-axis, and the way that you notice that is if you have reference peaks, so you have a reference material somewhere in the solution that you measured where you know exactly where the correct peak is, and if that doesn't match, you know, okay, there's a slight shift in the frequency axis and I know how much I need to correct it. So you just shift the whole spectrum a little bit. Then the second thing that you want to do is you want to remove unwanted peaks. So you, for the QMSA procedure or for creating a digital reference, you want to parameterize one specific chemical compound. And of course, in the sample that you're actually measured, there might be some other things. There might be this reference peak. There might be a water peak if there's a little bit of water. And there is, importantly, the solvent peak. of the solvent in which you have the compound, which will also react in NMR. So you need to remove them because you want to only characterize your actual compound or the spectrum of the actual compound. Then, as you can see, large parts of the spectrum here are already almost zero. And the reason they're not exactly zero is that one can have a baseline drift. So due to imperfections in the device, due to some noise in the electronics, you can have a drift of this baseline, so of the correct zero across the spectrum that you have recorded. And that can also be automatically corrected with a bit of fitting. And then you see large parts of the spectrum are basically zero. So we're not interested in them. So the next part of pre-processing that's important is to cut away the zeros, because they don't add any information. They just add potential noise and can lead to trouble. And you immediately see, okay, it's much nicer to look at the spectrum that we get, and it's nicer to parse the informations. And now there are basically just two steps left in the cleanup that we need to do of the data that we read in before we can really start working with it. And one of them you can see here. So you see here, this is slightly negative. So in principle, the correct NMR spectrum should never be negative. So what you predict from the parameters is never negative. And the reason you see negative values here is that you can have a phase mismatch. So in an NMR experiment, you send in pulses, magnetic pulses, to excite the material, and then you read out the magnetic response with an antenna. And if there is a slight mismatch in the phase of antenna and pulse you send in, you can get these negative artifacts, and you need to correct for this additional phase that might be in there, and this can be done. And then you get a positive spectrum, which then you can fit to the spectrum you predict from the QMSA parameters, which will always be positive. And with that, we are almost at the end. The only thing left to do is to normalize the spectrum so that we have the same units, that different spectra can be compared. And the standard is to normalize to the number of equivalent hydrogen atoms in the molecule. And with that, I'm also at the end of this small excursion, what is typically done for cleaning up spectra, experimental spectra, before you can continue working with them. None of this is new. This is all known, but it is something you need to be careful to do and implement before you continue with the analysis. And with that, I'm already at the end. Thank you, and I would hand off to Benedikt then.
Good afternoon, everyone. My name is Benedikt Schönauer. I'm yet another member of the Innovation and Outreach team, and I'm going to show you how we are actually now using all of this data that we analyzed before and pre-processed before in mixture analysis based on one-dimensional NMR spectra. That is an interesting and very practical problem. It means if we're given an experimental spectrum from somewhere, let's say all data on the internet, can we determine what is in this mixture? And ideally, can we determine how much of it is in the mixture? And one could say, yeah, this is a simple problem. I could manually integrate the peaks and I get some spectral weight that is proportional to the amount of hydrogens in the specific compound. And then by looking at the ratio of the peaks, I can determine, okay, this has this concentration relative to that concentration of another compound. But typically that doesn't quite work because peaks might overlap. There might be a baseline that is off, so then the integration doesn't quite give you the proper concentration. Noise might be a problem, and there might as well also be some peaks in there that if you integrate over, these are materials that are not part of the mixture but are solvents and so on. So what we're doing instead of doing this manual integration is we're modeling the mixture spectrum as a combination of component spectra. And these component spectra are calculated from accurate NMR Hamiltonian representations of the components. And these...
Say, Benedict, are you still on your first slide, or have
Yes,
you...
I am. I am.
Okay.
I'm still on the first slide.
Okay, very good.
Giving you the deal. And these NMR, I'm always trying to say HQS NMR, but these NMR Hamiltonians are obtained from this QMSA procedure that Nico talked about. And if we're doing this, then we need three things. We need experimental data that is useful and properly processed. We need very good component spectra. That means material-specific and solvent-specific NMR Hamiltonians. And we need to find some metric that allows us to automatically fit the component spectra to the experimental spectra and to evaluate how good this fit is. But let's talk about the experimental data first. I mean, much of what you see on here is the workflow for cleaning up raw experimental spectra, and Nico has already talked about. But I want to kind of begin at a step before that, because we get all of these data from different vendor-specific data formats for the spectrum. So there are many different vendors out there, and all of them store their data not just in some text file with frequencies and intensities, but in typically even spectrometer-specific data formats that encode the intensity and frequency, but a lot of other metadata. And we need this metadata in order to do our quantitative analysis. So the first step is already importing data from all these different spectrometers and turning it into a common and standardized internal representation of a spectra that is the same for all of them, and to validate this data, to make sure that we read in everything correctly and that all the required info, like spectrometer frequency, like solvent, are present and can be used in the further quantitative analysis. So what you see here is the spectrum, the mixture spectrum of two components in a 1-to-1 ratio. We know from the company that provided this data, this experimental data, that there's a 1-to-1 ratio between the two, between this 3-aminobenzyl alcohol and ethyl 3-aminobenzoate. And what you see here in black is the raw experimental spectrum, and in orange is the spectrum after all this pre-processing that Nico has talked about has been performed. The only thing that I did to this black spectrum is I normalized it so that they lie on top of each other. And the first thing you can already see, even in this very broad range from 1 to 7 ppm, is the solvent peak has disappeared in the process spectrum. For everything else, we have to zoom in a little, so we're doing this. So now we're just in the ppm range of 2.1 to 2.8 ppm. The gray area is the solvent peak that we're removing, but you see other things here as well that we need to clean up first. One thing is the noise. So you see a lot of small wiggling, which, I mean, if you just look at it, it's not very distracting, but of course we're trying to do something automatic, and all of this might interfere with getting the correct spectral weight automatically. So ideally, we want to remove this noise so that it's a smooth function and doesn't suggest some spectral weight where there actually isn't any. And the other thing that you see here on the right is this baseline problem that Nico has pointed out. We have values below 0 and above 0, and even a slope to the spectrum, and all of this shouldn't be here. We should have 0 spectral weight in areas where there is not a resonance. So here you see that even in practice, even for this rather good spectral data that we got, we have to do all this cleanup first. But now, with this in mind, let's go to the actual, let's get back, go to the actual mixture analysis. So here I show you again the same experimental mixture of these two compounds of 3-aminobenzyl alcohol and ethyl 3-aminobenzoate. But now I started with some initial guess. I put in an initial guess where I said, okay, I'm going to assume there's 10% of aminobenzyl alcohol and 3% of the 90% of the ethyl aminobenzoate in there, and then just looked at the component spectrum, which is just the sum of the individual spectra that I get from solving this NMR Hamiltonian multiplied by their concentration. And I compare this with the mixture data. And it suggests that it's actually a really good fit, that this might actually be already what I'm looking for, that there might be 90% of aminobenzoate in there and 10% of the aminobenzyl alcohol. But we have a fit metric here, which is the Wasserstein distance, which is a measure for how much you have to modify one spectrum to end up with another spectrum. So a Wasserstein distance of 0 means these spectra are identical, and everything higher than that means, okay, I have to modify this a bit in order to get to the other one. And here we already have like a fit of 82%, which suggests that this might already be the result. But this is just the lower part of the chemical shift range. And you have to look at the whole thing. And then in the upper part of the ppm range, we find there are some rather indicative peaks, which stem from the from the aromatic rings. And here we see, okay, indeed, there is some spectral weight that is not accounted for by this ratio of components in the mixture. So now, after this initial guess that I just put in my hand myself, we're doing our automated mixture analysis, quantitative mixture analysis, and see what we get there. And this automation tells us, yes, there's 51% of the 3-aminobenzyl alcohol and 49% of the ethyl 3-aminobenzoate, with a slightly higher fit quality of 84.8%. And whereas the previous spectrum, where I just guessed something, looked very good in this ppm range, this fit, this automatic fit, where I did not input anything, I just said analyze this and optimize the Wasserstein distance, this fit looks worse in this range. I mean, most of the spectral weight is still somewhat accounted for, but we can then look at the upper range of the ppm range, and here we see, okay, even these characteristic aromatic ring spectra are now accounted for and with a proper ratio. And I mean, we know that this is a 1-to-1 ratio, so our automatic workflow has recovered the proper ratio of components, whereas if I just did it by hand and looked at the spectrum, I would have been dead wrong. And this already brings me to the summary. So reliable mixture analysis has to start with some reliable experimental data. You've seen that. We have to post-process this experimental data, otherwise we can't really do the fitting, and you should have an objective fit metric, otherwise you might end up with quite wrong results if you do it by hand. And that's it from my side.
Yeah, thanks, Benedict. Yes. Okay, so we have now walked through data for UV-Vis and QMSA, ideas for molecules, smaller molecules in that case, but let's now get to really large molecules, proteins, also quite important on a technological level. And I will discuss a little bit how we recover data from this and how this combines ideas we have seen from data handling, but also from using parameters. So what I'm going to show is a comparison. So from quite old data, I'm going to use so-called BMR-B shifts. So anybody who has looked at NMR data from proteins probably knows this database. The BMR-D database contains these so-called chemical shifts. What it does not contain is the couplings between the different spins or the different spin species. And this will become important in a second. Then, of course, I'm going to look at data that is from 2006. So people measured a protein in 2006, and this data is today available on a database called Zenodo. People might also know this. This is a general database that is used quite heavily to store data from scientific publications. And of course, now 20 years later, we would like to use it. And let's have a look what needs to be done to make that possible. And now, let me first, since not everybody is probably here deeply involved in protein NMR, give you a feeling of what we are doing. We look at a protein called ubiquitin. This is a typical protein exactly for purposes like we have here, for giving a webinar or writing a paper on methods. So it's a very common and well-measured protein. And the type of spectroscopy is called HSQC. And it's a type of spectroscopy that reveals the coupling between kind of the protons and 15N, so 1H and 15N, and for basically the amino acids. And this is a typical thing because, okay, taking just a 1H spectroscopy for a protein is not so super informative. You can imagine that to be very crowded. In fact, what I showed you at the very beginning of this webinar was this very crowded 1H spectrum for the same molecule here. So that is why there are lots of techniques where you try to filter out specific parts of the couplings and the specific parts of the kind of protons. So yeah, this is the type of data, the chemical shifts from BMR-B, and the experimental HSQC. Fun fact also that the data was taken on a Varian machine. So some people might also know that. So Varian is today bankrupt provider of NMR devices. So like 30 years ago, you could buy a Varian NMR device. And the data is in frequency domain. So in free induction decay, so in time domain. So it's time domain data that is available, and from a device that from a kind of a company that does not exist anymore. Nonetheless, this is still a quite common problem that people have a lot of variant data since these devices were quite common in the past. So looking into it can be quite worthwhile. Now, we already start and look basically at the conditions that are fortunately recorded for the BMR-B, of course. I mean, that is, of course, always well documented where the data comes from. And fortunately for the data that we got from Zenodo, it's also recorded. What we see is that the solvent is different, and that's quite meaningful difference. That also means that the final result will not be completely comparable. So we will not have a complete one-to-one comparison, will not be possible immediately for the Zenodo and the BMR-B parameters. Because the difference between having something in H2O or having it in D2O is just a little bit too large. But there should still be a broad agreement of the data. Also, of course, the temperature difference also makes a difference, and we do not know how pH compares. And now, if I mean, if you start this and take maybe a naive approach to plotting all these data, of course, I show here something that is pretty bad to show you how you can then step by step improve. But what was done here was basically you take the BMRB shift and look at every case where you have a 1H and a 15N and look at their frequencies. So here we have a frequency axis for 15N, and here we have a frequency axis of 1H, and the orange points are basically points for each of where you have combinations of these two. So lots of points, and then the blue is basically the first quick guess of plotting the Zenodo data, and I will come in a second a little more where this comes from. But what you see that there is no comparison whatsoever. It's like completely off in every way. But like the first step then, of course, is improving the BMRB plotting of the parameters. Now, BMRB data is considered to be highly precise. Yeah. So there shouldn't really be any problem with that. And what needs to be done is you need to filter the pairs of 1H and N, 15N, down to the ones that actually couple. So you need to look at the chemical shifts, compare it to structural data from the molecule that is normally also available, and then basically filter out all these points where you actually have kind of a one bond away coupling where the H directly couples to the 15N. And this was done here. And we can do this, of course, in an automated fashion, such that you directly get it down to the backbone and to the NH pairs. Of course, you also only keep the larger coupling constants, but this just means you keep like the nearest neighbor coupling, which you can also estimate from the distance or from the fact that in the structure they are close. Now, why was then the 1H axis of the comparison so off between the variant measured data from Zenodo, blue, and the orange points from BMRB? So old variant data, the free induction decay data, time domain data, if you Fourier transform it, you don't immediately know what is the center frequency. So there's no obvious frequency scale that centers it. And what I showed you initially was an approach where you use a carrier-centered approach. So carrier-centered means you have an input frequency, and then you just say, okay, I have a certain range of my spectrum. So that is given, and I have a carrier, and then I just take this as the middle and then just take around it. And this is, of course, completely wrong, or was also completely wrong. And you can see it because basically the range of your frequencies is kind of wrong for what you expect from a protein. But also you can compare it to the BMRB values and also see that this is wrong. And so you need to do it differently. Now, very well-known tool, NMR Clue, does not work at all on this. In principle, it is supposed to work on variant data, but it didn't here. The original work was supposed to contain a file called NMR pipe, but now it has been reshuffled several times and the people who took it are retired. So now this was also not available. Fortunately, in the variant data, you find the so-called procpar file. And there you can look up the parameters, which we do in an automated fashion. And there, after kind of going through several steps of what's possible and what should be done, and there you find the RFL and RFP, which is the beginning and the end. And then through this, you can kind of correct it and bring it back in shape. Similarly, for the 15N, axis. So there are several frequencies given as reference frequencies in these old school files, where you have to find SFRQ, DFRQ, and a DFRQ2. And through this, you can identify the 15N frequency, which normalize it now. Then last check is, do we see somewhere an obvious water feature? I mean, even in D2O solvent, we would expect a remnant water feature. And from the experiment, we expect that there should be a water dip from a saturation experiment to get rid of the water feature. But if we look through and see where we could find it, there was nothing obvious. So it didn't seem as if this was in contradiction to our axis. And at the end, this is where we end up with the BMRB data on top of the measured spectra. And we can now see that there's still an offset, of course. The kind of measured data and kind of contains a lot of features, additional features, but up to the point where we would expect a similarity given the difference in the solvent, we have achieved comparability. So just to walk you through to this case, in some sense, if we use legacy data, you have to identify where it comes from. Parse the old formats, very funny in that case, having to look through old variant data. Of course, look at the conditions. The reconstruction of the ppm axis can be surprisingly complicated. Looking at the water dip to check if something, or the water peak, if you had a solvent feature. Looking for that can be quite important as well. And of course, if you compare to something like the BMRB chemical shifts, and you look at 2D spectroscopy, you have to still pick out the structural information from somewhere else, and then at the end compare. And this, of course, what we can also do, and what we can do for you, is recover old data soon. We will also provide Gibbon as a tool to recover data for PDFs, harmonize it into common metadata and other referencing units. Very important, parameterize it, and this can then lead to automated workflows that you can use again and again and again. With this, let me just come to an end. If you're interested, or if you work in NMR, don't hesitate to sign up to our end-to-end NMR tool, HQS Spectrum. You'll find here HQ Spectrum, the address, and you can also contact us if you're interested in this topic or anything I discussed today. With this, we are at the end of the webinar.